So I think this one's a bit of a weird question, but let's take a look at it nonetheless. So the relative housing cost for a U.S. city is defined to be the ratio between the average housing cost for the city over the national average housing cost. Okay, so it's just comparing the housing cost in a city to the national average. Okay, and it's expressed as a percent. So uh, so you can have what do we have here? So percent of national average cost. So we can see here, for example, that like this city right here is a little bit over 200% of the national average. What does that mean? That means it's a little bit over double the national average housing cost. Okay, so, and we're comparing it to the population density here. And we're told that, okay, so it shows the population relative housing cost and on the y-axis and the density for several large cities in the year 2005. We're told this equation of the best fit line, and we're told, or rather being asked, which of the following best explains how the number 61 relates to the scatter plot? Well, so let's remind ourselves that this is a linear equation, so y equals mx plus b. So 61 is the b value, that's our y-intercept. And we can also figure that out just because if we plug in 0 for x, 0 is where the y-intercept occurs, you will get y equals 61, which we see right here. So basically, we're being asked to interpret this. Let's take a look at the options. A. In 2005, the lowest housing cost in the U.S. was about $61 per month. The problem with this is that none of the units on the x or even y axis are in dollars. Okay, so here you have the units are percent, and here you have people per square mile. So there's just nowhere that you can get dollars in terms of your units for your answer. So we're going to have to throw A out for that reason. We see, however, that for B, C, and D, all of them are in percent, so at least there's that. So let's take a look at B, C, and D. B. In 2005, the lowest housing cost in the United States was about 61% of the highest housing cost. We can't really determine that. All this means, so a line of best fit is just a line that tries to describe the data that you're given and then helps you make predictions based on that. So we basically the reason B isn't the answer is just because we don't actually have a point here. If we had a point that represented a city right here, then that would maybe be an answer, but in this case it's just not. This line represents predictions because you put in all these points, you're given this best line of fit, and based on this you can say, okay, at this population density I predict approximately this relative housing cost. So again, the line represents prediction based on data rather than data itself. So we can't say B because we don't actually have a point there. C. In 2005, even in cities with low population densities, housing costs were never below 61% of the national average. Okay. That probably isn't a very good conclusion either. So we're getting to pretty good wording here with C. I mean, so we're talking about sort of housing costs in low population density areas, which makes sense because again we're comparing population density to the housing cost. But a statement of housing costs were never below 61% of the average. You just can't make that statement based on this. Again, this line just represents a prediction. We see here that there are points on both sides of the line. There might be a city like right here. We don't know that. We can't make this. Basically, the word never is a very strong word, and based on a linear regression like this, you can't say never because it's just a prediction. D. In 2005, even in cities with low population densities, housing costs were likely at least 61% of the national average. That sounds much more reasonable. Again, the word never is very strong, and we don't see that here. It's 61% right at the y-intercept, right? And of course, it doesn't make sense to say that at a population density of 0, there's this housing cost, because if the population density is 0, then there's no people. But the point here is that we see this line moving towards this point in the low population density sort of range of the x-axis. And so with this, we can say, or we can predict that in this year, even in these cities with low population densities, it's very likely that they were at least above this point, because our regression says that you're supposed to only reach this point if you have a population density of 0. So D is our answer. If we quickly go over at least how you can get it by elimination, then this one is by units. This one is again, an exact statement, which we can't get from a regression because this line regression is a prediction. C is also a very exact and strong statement, which we again can't support with merely a sort of statistical prediction. But here with the we're likely at least 61% of the national average, that we can actually draw from this line. So D.